Welcome to this lecture. So in this lecture on Laplace transform and differential equations, I'm going to take up three differential equations and compare the solutions, the nature of solutions, compare the nature and behavior of the solutions of these three differential equations. These three differential equations have already been solved and the solutions have been found out in my previous lectures. I think they are part 7 and part 8 and part 9. These links for these part 7, part 8 and part 9 where I solved these differential equations are given below in the description. So now we will take up their solutions. I will just take up the solutions from those lectures and compare their behavior and nature. Okay, we will go on to the solutions. So the first equation is this: d square y by dt square plus dy by dt plus y equal to 1 with these conditions. So when we solve this, we got this equation ys equal to this. Actually this is ys only. For clarity, actually this is ys. So this is ys only. For the sake of clarity, because I am going to compare three differential equations, I have taken it as y1, and later I will be taking second equation as y2s and so on. So this is actually y of s only. This y, when you take Laplace transform of this, we got y of s as this in the previous part. So for clarity, in this lecture, I have taken it as included as subscript 1. So I'll call it as y1 of s, and the solution, the inverse Laplace of this, we got this. Okay. We got this as the solution, as the inverse Laplace of this. Similarly, the second equation was this: d square y by dt square plus 2 dy by dt plus y equal to 1. The initial conditions were 0. So here we got earlier ys as this, and since this is equation 2, I am using a subscript 2, y2s equal to this, and this inverse of this solution y2t is this. And similarly, third equation is this: d square y by dt square plus 3 dy by dt plus y equal to 1. The initial conditions are 0 as before, and here we got ys, y of s is this. And for clarity, because I am considering three equations, y1 or 2, 1, 2, 3, so consistent that this is equation 3, that this represents equation 3, so I am using a subscript y3. So the inverse of this is found this. Now what will be the nature of these three equations: y1t, y2t, y1, y2 and y3? So before understanding this, before coming to the nature of these roots, so let us find out what will be the roots of this equation. See, every term, every function y1s or y2s or y3s has a quadratic term in the denominator and also an s. So let us leave out this s right now. Let us concentrate on the quadratic term. So you have a quadratic term, s square plus s plus 1 here, and here you have s square plus 2s plus 1, and here you have s square plus 3s plus 1. So what will be the roots of these equations? So here if you see this equation, s square plus s plus 1, and if you find the roots, these roots are going to be complex. This will be a complex roots. And the real part of this complex root will have a negative number. The real part is a complex root. This equation s square plus s plus 1 equal to 0 will have complex roots with the real part as negative. So in such a case, the response equation, the equation solution will be equal to this. What does it have? So it has a cos plus sine term multiplied by an exponential term. This exponential term is e power minus t, so it's a negative power, it's a decaying term. So what are the characteristics of this? If I plot y1 versus t, how does it look? See, what is the initial value? Initially at t equal to 0, if you put t equal to 0 here, what will be y1? Y1 will be 0. Okay? If you put t equal to 0, y1 will be 0. If you put t equal to infinity, what will be y1? What will be y1? If you put t equal to infinity, if you put t equal to infinity, this term will become 0, whereas these two will be finite. So it will be 1 minus 0, so y1 will be 1. So at t equal to 0, y1 is 0, and t equal to infinity, y1 will be equal to 1. But in between, so it starts from 0 and ends at infinity. But in between, what will happen is because of this presence of sine and cos, there will be oscillations. You know, sine and cos functions have oscillations, so they'll have oscillations, and because this cos and sine are multiplied by this exponentially negative term, the oscillations will continuously decay. That is, the amplitude of these oscillations will continuously decrease. So with this, let us make a plot. Let us make a sketch of y1 versus t. Let us make a sketch of y1 versus t. Yes. So if you make a sketch of this y1 versus t, so this is y1 on the y-axis, and we plot y1 versus t here. This is the ultimate 1. This is 1. So the curve at t equal to 0, y1 equal to 0, and at t equal to infinity, it reaches 1. In between, it's going to oscillate. So ultimately, it reaches 1 here, but in between, it will oscillate. It is going to oscillate. So starting from 0, it is going to behave like this, oscillates, and the oscillations continuously decay. That is, the amplitude of this oscillation will continuously decrease. So this is the highest amplitude, then decreases, then decreases, then decreases. Ultimately, it will reach, when t equal to infinity, it will reach this constant value y1 when t equal to infinity. That is this. When t equal to infinity, it will reach 1 at t equal to infinity. So this will be the behavior of this equation. This equation is going to behave like this. Okay, now let us consider the second equation. So second equation is this. It is almost similar to this, almost same. What is the difference? Initial conditions are same, everything same. The difference is this. Here the coefficient is 2 here, and here is 1. Now what will be the roots here? What will be the nature of roots here? The roots are going to be real and equal. So the roots are going to be real and equal, and will be negative real numbers. The roots will be real, but negative real numbers, equal, real and equal with negative value for negative factor of this is a negative real number, equal roots. So the roots are real and equal, and the real part is already real only, negative real. In the previous case also I told you roots are complex roots, but the real part will be negative. So in both cases, the roots will lie on the left half of the complex planes. Complex plane means this is a complex plane, this imaginary axis, plus, minus. So previous case, complex roots, they'll have negative real parts. So the roots will lie here, somewhere here, negative side. And in this case, real and equal, but negative real numbers. So it will lie on the real axis on the left hand side. So the solution for this we found as this, y2t equal to 1 minus ct into 1 plus t. So the roots are real and equal. The solution was this. So what is the nature of this equation? These are only exponential negative term. There is no sine or cos. You have only this term, e power minus t, exponential term. No sine or cos like here, like in the previous case. So a plot of y2 versus t, how does it look? Here also you find that the same, when t equal to 0, and t equal to 0, what will be y2 equal to 0. When t equal to infinity, y2 equal to 1. Like in the previous case, here also it is going to start from 0 and end at 1. But how is it going to behave? How is it going to behave in the in-between period? So let us see. Let us plot and see. So a plot of this equation, is going to look like this, starting at 0 and ending at 1. But since there is no sine or cos term, there is no oscillations here. This is exponentially decaying function, the second term. First term is a constant, so 1 minus a decaying term. So it's going to be it's going to rise from 0 to 1. So ultimately it will reach 1. This is 1. This is 1. Okay. This value is 1 there. So it rises from 0 to 1. This value is 1. So ultimately it reaches 1. See the contrast between this and previous one, where when the roots are real and complex, the response, the solution y1t, nature of solution is, the behavior of or nature of behavior of solution is continuously oscillating function, but with oscillating continuously decaying, the amplitude decaying, and finally ultimately reaching the constant value 1. But here there are no oscillations in this. The roots are real and equal. Still they lie on the left half of the complex plane. There is no sine or cos term, there is no oscillation, and there is only constant gradual rise from 0 to 1, like this. Okay, now let's go to the third equation. So again, this is the third equation. The only difference is this coefficient is 3 here. The second coefficient, this is 3 here. The first case it was 1, second case it was 2, third case, this is third equation, this is 3. All other factors are same. So here we got this y of s equal to this, and what will be the roots here? The roots are, what type of roots are going to get for this term? For this term, what will be the roots? Roots are real and unequal. The roots are real and unequal, right? But still the real part will have negative number. The real part of the root will be negative. So it is going to lie on the, like in the previous case, real and unequal roots, they will lie on the left half of the complex plane, because the roots real part will be a negative number. So in all the cases, with all the three cases, the roots lie on the left half of the complex plane, or this is imaginary axis, this is the real axis. So all these three cases, the roots lie to the left of the imaginary axis in the complex plane. Fine. So when the roots are real and unequal, this is the equation we got in the previous part. When you derive this, you have derived this equation we have derived. So this equation is a derived equation, that is, this is nothing but the Laplace inverse of the inverse Laplace of this. Okay, so here what you have a cos term, cos h hyperbolic cos plus sine hyperbolic sine multiplied by e power minus term. So this e power minus term is common in all the three equations, right? So this is an exponentially decaying term. So what will be the values when t equal to 0? Again, what will be y1? Sorry, this is y3 here. This is y3. Y3 is going to be 0, because when t equal to 0, sine 0 is 0, this is 1, but this is 0, right? Sorry, this is e power minus 0 is 1, this is 1, this is 1. So this whole term will be 1. This is 0, 1, 1. When t equal to 0. So the whole term will be 1, 1 minus 1, 0. Right? When t equal to infinity, this term will be finite, but this is e power minus infinity is e power minus infinity is 0. So because of that, this left second term will be 0. So you are going to be left with 1 only. So y3 will be 1. Okay. So when the roots are real and unequal like this, so you have a cos h and sin h terms in the solution, and these are the initial value. T equal to 0, it will be y will be 0, and t equal to infinity, y equal to 1. So in between, how does it behave? This cos h and sin h multiplied by e power minus 3 to e power minus term. So how does it show up in a sketch? Let us see. So if you make a plot of this y versus t, it's going, this is t here, the y-axis is t. For comparison, I have shown the previous graph also, previous equation y2. This is y2, right? So this is y2, previous one. I have plotted on the same graph. I drawn the sketch on the same graphs to understand the difference between second equation and third equation. So this one, this equation, this is third y3. This will behave similar to y2, starting from 0 and ending at 1. This is 1. This is 1. This value is 1. It starts from 0 and reaches 1 ultimately. But it is similar to y2, but the difference is it is going to rise much slower than y2. So the function, the y3 is going to rise to the ultimate value, final constant value of 1, but at a slower rate compared to y2. Otherwise, the nature of y2 and y3 are similar, starting from 0 to reaching 1 without any oscillations. Between y1 and y2 and y3, y1, all of them start from 0 and end at 1, but y1 has oscillations in between. y2 and y3 have no oscillations. So y2 reaches 1 faster than y3 without oscillations. So y3 becomes slower than y2. So this is the comparison of the nature and behavior of the solutions for these three differential equations. So let me summarize. All the three differential equations looks almost similar. The initial conditions are same. The only difference is the coefficient of the first derivative dy by dt is different. And in all the three cases, you have a quadratic term, get a quadratic term in the denominator, and also s. Right now s, we will leave out s. Let's see the significance of the quadratic term. This quadratic term has, all the three cases, they have roots with negative real parts or negative real numbers. So in one case, the roots are complex. In the other case, the roots are real and equal. In the third case, the roots are real and unequal. When you have complex roots, and all the three cases, the equation, the solution rises from 0 at 0 time to a final value of 1. But when the roots are complex, there are going to be oscillations, and successively the oscillations decrease and decay to a constant value. When the roots are real and equal, there's no oscillations. The y value rises smoothly and we'll say little faster compared to the third case. It rises faster without any oscillations and reaches the final constant value. Third case, when the roots are real but unequal, you have a similar nature, starting from 0, reaching the constant value without any oscillations, but it becomes slower compared to the second case, and the roots are real and equal. So this is about the nature of the solutions and how they differ with respect to the roots of the quadratic term in the denominator. So this will serve as a small introduction to what is going to come up later in when you study analysis of the analysis and dynamics of processes and analysis of control systems. So there you will be studying more of such behavior, which is better, which is good, which is not good for control systems, etc., etc., and what makes this response, or what makes this equation y behave like this or like this or this. So we'll be studying more in detail, more in depth in the later when you go for higher order systems or control system analysis. So for that, this lecture will serve as a small introduction with respect to the nature of the solutions of the equations based on the roots of the quadratic term in the denominator of YFS, that is Laplace transform of the solution. I hope it is clear. And as I said, the links for the solution of differential equations are given below in the description. You can go through them if you have not already gone through them. Okay, so we'll come with more lectures, more classes, more information on Laplace transform in the coming lecture. See you till then.